Right. Okay, in this talk I'm going to discuss event history analysis, talk about when it's used, and in particular why we need special regression techniques, why you can't just use ordinary multiple regression to analyse event history data. I'll then go on to just give you a few examples of the sort of research question that you can answer using event history analysis. I'll talk about the event history data, possible sources for the data, particularly in the UK. And then I'll go on to discuss methods of analysis. And I'll start off with descriptive methods, which is where we should always start. And then I'll go on to modelling techniques where you're bringing in covariates and looking at the effects of those on the timing of some kind of event. And then at the very end, I'll just say a few words about further topics, just as Bill did, okay, where you might want to go next. And also a little bit about resources that you can look at to learn a bit more about this technique. All right then, so what is event history analysis? Well, in an event history analysis, the dependent variable is the duration until some kind of event occurs. Right? So what you're analysing is the length of time between when somebody becomes at risk of experiencing the event and when they actually experience it. Right? And it goes under a lot of different names depending on what discipline you come from. So these techniques really grew out of biostatistics where the event of interest was death. Right? So that's where the name survival analysis comes from. Right? So you're interested in the amount of time that people survive until they die. In economics, they talk about duration analysis, and in some other disciplines, demography, for example, they talk about hazard modelling. Right? These are all really the same technique. In social sciences, we tend to use event history analysis as the name because very often the kind of events we study in social science are repeatable. And there you're interested in the whole event process. Right? So that you might have repeated spells and you want to look at all of those, not just the first occurrence. Okay, here's just a few examples from different disciplines in the social sciences where you might want to use event history techniques. Right? So in education, for example, you might be interested in the time that somebody leaves full-time education. Right? And there, the at-risk period, if you like, might begin at the time when they finish their compulsory education. Right? In economics, there's an awful lot of work looking at employment transitions, and there, the kind of event of interest would be the end of an unemployment spell or the end of an employment spell. All right? So you're looking at duration of unemployment spells, duration of employment spells. In demography, you might be interested in the birth intervals, timing of births, right? The time that somebody first partners, be that marriage or cohabitation, and the time to divorce. Right? And then in psychology, duration to respond to some kind of stimulus. Now, in many of these examples, it's clear when somebody becomes at risk of experiencing the event. Right? So, for example, if you were studying divorce, then somebody becomes at risk of experiencing divorce when they marry. Right? But there are some kind of events where that's not always that obvious. So I've got a question mark there for time to first birth. Now, in countries where people only have births within marriage, then that's straightforward. You could use the age at marriage as a starting point. But in countries like the UK, this is more and more difficult issue. And that's a sort of substantive question you should think about. What is an appropriate origin? Right? Would it be age 16 or younger? Right? So that just needs a little bit of thought, and there's no right or wrong answer. All right, types of event history data. Okay, what we need to construct durations are dates. So we need to know when somebody becomes at risk, that is the start of the exposure period, and also when they have the event. And for example, in an employment spell, you need to know when they start employment, start a particular job, and also when they leave that job. And very often, these data are collected retrospectively. So you might interview a person at one point in time and ask them to recall the dates when they became at risk and when they had events. Right? And this is very common, for example, in the British cohort study. So you've got certainly the 58 and the 70 cohorts. You have event histories that are collected. You have their partnership, cohabitation, marriage histories, their birth histories, employment and housing histories. And in the 1958 cohort, for example, people would be asked at age 33 for all the events that occurred since the age of 16. And then they were interviewed again at age 42 about events that had occurred since age 33. So retrospective data is very common, but you can also get event history data through prospectively collected panel data. So for example, the British Household Panel Study. So there you might just have employment status, for example, at each wave, which are annually spaced. So there you don't have problem of recall error that you would in retrospectively collected data, but you might have some loss of accuracy in terms of when your information about when events occurred. And in the BHPS, incidentally, we also have retrospectively collected data. So BHPS started in 1991, so you've got current status data from that point, but then in 1992, people were asked about their full birth histories, employment histories and partnership histories. So you have the full history right from the age of 16. All right. So these are the different sorts of data. And I should say that if you're embarking on an event history data analysis, then by far the most time-consuming part is getting your data into shape. I mean, that's always the same with statistical analysis, but particularly the case for event history data. But hopefully I'll convince you that there is substantial trade-offs. And once you've done the data prep, then the analysis is usually fairly straightforward and the quick part. All right. All right, so why can't we just use standard regression techniques with event history data? Well, there's three main reasons. One is that durations are never going to be negative, right? And also they tend to be positively skewed, because what you find is that as you go through time, you get fewer and fewer events. Right? Now that's not too much of a problem, because if you were using regression, you could do some kind of transformation, a log transform, so that you get rid of the skew. The next two issues are more problematic. The second one, censoring. This is when you have incomplete duration information, and the most common form that takes is what's called right censoring, and that is when there are individuals who have not yet experienced the event by the time that you observe them. Right. So, for example, in the 1958 cohort study, let's say you were using data collected at age 33 and you were looking at divorce, well, there'll be a lot of people who haven't yet divorced. Right? They might divorce in the future, they might never divorce, but you just don't know. So their duration to divorce is right censored. The other reason for using special techniques is that very often you have longitudinal data on your explanatory variables, your covariates, and you want to include that in some way in your analysis. Right? You don't want to just fix the value of these variables at some arbitrary time point, for example, the start of the observation period. You want to use information about changes in covariates and see how that predicts the timing of the event of interest. Right? So if we were just looking at whether somebody is divorced or not at a particular point in time, we lose all of that information. Right? So we have to consider something like divorce as a dynamic process, which can depend on changing variables. All right, a little bit more about this censoring problem and why we can't just ignore it. So I mentioned that right censoring is by far the most common. So let's suppose you are studying divorce. You've got a large number of people who are going to still be married by the time that you last observed them. Now, one approach might be just to get rid of those observations. Okay? But the problem with that is that, first of all, you're going to drastically reduce your sample size, okay? Because you're going to kick out of your sample of all those who are still married, which is going to be a substantial proportion. But also, it means that you're going to bias your sample towards people who experience the event early. So in this case, you'll be biasing the sample towards people who both married early and divorced early, and they may be very different from the population at large. Right? So analysing that subgroup can give you biased results. Okay, so what any any event history analysis technique will do will be to incorporate these right-centered observations. And it will usually do this under a certain assumption. And that is that censoring is non-informative or random with respect to the timing of the event. Now, in most social science cases, that's quite a reasonable assumption to make, because usually the end of the observation period is corresponding to the time of interview. And the timing of the interview is really a random event in terms of the individual, in terms of when they have events. Right? So that assumption is not usually a problem. Where it might be a problem is in experimental studies, for example, in clinical trials, where you're following people through time, and perhaps it's those who are most at risk who drop out of the study, for example, because they have side effects. Right? And then if you don't take that into account, you would then overstate an effect of the treatment. Right? But in social science, by and large, this non-informative assumption is quite reasonable. All right, a little bit of notation so we can get going on the analysis. You can define for every individual an event time, right? TI, but alongside that you have an indicator which tells you whether or not they had had the event by the end of the observation period. So that's coded 1 if they're uncensored, in other words, they have the event, and 0 if they are censored. But this event time is not going to be completely observed for those who are censored. Right? So if C is equal to 0, we don't actually fully observe TI. What we actually observe is the minimum of the event time and the censoring time. Right? And that's what I've called YI. So the data that capture the most important part of the event history in terms of the timing of the event are the smaller of the event time and the censoring time Y, and this censoring indicator C. Right? So in any event history data set, you will always need those two pieces of information. All right, now key quantities, things that we might want to calculate to tell us something about the timing of an event. Well, there's two quantities that people usually focus on. The first is called the hazard function, and I'll denote that by H in T in brackets. And the T in brackets just tells me that it depends on time, the time since they became at risk of having the event. And then you've got the survivor function, which is denoted by a capital S and T. So the hazard, that's a conditional probability. It's your probability of having the event at a time T, given that you haven't already had it before that point. Right? Now, the survival probability is the probability that you haven't had the event before time T. And this language, survival, that's coming from the biostatistics literature, where the event is death. So if you haven't died, you've survived. Right? So it's the proportion who have not had a death before time T. Now, in practice, people often focus on the hazard function. The hazard function can move up and down over time. It doesn't have to always increase or decrease. Whereas a survivor function, that has to always go down, because as you're going through time, you've got a smaller and smaller proportion who are surviving. Right? So that's less interesting to look at, although it can be useful to compare that across different subgroups. But the hazard function is the thing that's going up and down. All right, so now moving on to a little bit of analysis. I'm going to start off descriptively and talk about a method called life table analysis, and this really comes from the demographic literature. So the first stage of a life table analysis is to group your durations into intervals. Let's say these were yearly intervals, and you denote them by T, 1, 2, and 3. Now, for each of these intervals, we can observe three things. The first thing is the number who are at risk of having the event at the start of the interval. That's RT, R for risk. The second quantity is the number of events that have occurred during the interval. And again, this is coming from mortality literature. D stands for death, all right, but it's number of events. And then you also have the number who are censored, so the people who are withdrawn, if you like, from the study in a particular time interval. And a simple estimate of the hazard function, the probability of having an event, given that you haven't already had it, is simply the number who have the event in an interval divided by the number who are at risk, so D over R. And in practice, what some people often do is make a correction for censoring. And that's because of those who are at risk at the start of the interval, some of them will be censored at some point during the interval, so they're not at risk for the whole interval. So people just have a slight adjustment for that. But that adjustment doesn't really make that much difference, because what you're interested in is looking at patterns in the hazard over time, okay? Not necessarily the absolute values that the hazard takes. All right. Now, once you've got the hazard, you can directly calculate the survivor function from that. And what that is, remember that the survivor function is the probability of surviving beyond interval t. So what that is the probability that you don't have the event in time interval 1, that's 1 minus the hazard for time point 1. You don't have it in time 2, and so on, you don't have it in time t minus 1. You just multiply all these together, and this second formula is just another way of expressing that can be quite useful when you're doing computations. Right? You can just think of it as a product of 1 minus the hazards. So for example, if you want the probability of surviving to the start of the third interval, it would be the probability of not having the event in the first multiplied by not having it in the second. All right, to give you an example just to show how this works in practice, and these data come from the National Child Development Study, I mentioned that earlier, also known as the 1958 birth cohort. Right? So the respondents for this study are all born in a particular week in 1958. Right? So when they're interviewed, age 33, they're all the same age. They were, I think, most recently interviewed at age 46. And I've just taken a subsample from this data. So what we have is time to first partnership, and they become at risk, if you like. The way that we've defined the risk period is to start at age 16, right, when they could become legally married. But we're also looking at cohabitation here. So we observe them from 16 up until age 33, and this is the number at risk, and it starts off at age 16 at the total sample size of 500. And then if you go through time, here we've got the number who entered their first partnership. So at age 16, 9 of them entered their first partnership. All right? And then of those who remained unpartnered at age 16, 20 of them partnered at age 17. All right? And this is the number who were censored. And because this is a birth cohort study, you don't actually have any censoring until the final age. More generally, if you had a sample which had people of mixed ages, then you would have some numbers in here that were non-zero. But what we can say from this is that by age 33, only 35 of the original 500 had not yet partnered. And from this information, from R, D and W, you can calculate the hazard function and also the survivor function. So survival here is having survived not finding a partner, all right, and not entering a co-residential union. That's how a partnership is defined. All right. So you can see that by age 33, 7% have remained unpartnered. A few examples on the next slide just to show you how these things are interpreted. So at the very first stage, you've got the hazard for age 16. 0.02, so that's telling you that 2% partnered at age 16 before their 17th birthday. If you jump down to age 20, you get a hazard of 0.13, so that's saying that if you hadn't partnered before your 20th birthday, then you have a 0.13 or a 13% chance of partnering before your next birthday, your 21st birthday. And then finally, you've got an example of the survivor function there. So you can say that 77% had not partnered by age 20. All right. And directly from those results, we can do a plot. And this is usually how you would look at the data rather than looking at it in the tabular form. Right? And so what you can see here is that the hazard of first partnership going from age 16 up to age 33. And what you can see is that the hazard increases and then it starts to go down. Okay, so up until, I think it's around your early 30s, right, your chance of entering first partnership increases with each year. Right? But if you haven't partnered by age 30, right, your chance of partnering starts to go down. Right? This is at least for the 58 birth cohort. If you're looking at the 1970 birth cohort, you find a similar pattern, but it's shifted along a bit. All right. So you don't have to give up hope at the age if you're age 30 if you were born in 1970. Okay. And the survivor function, well, that's not so interesting to look at because we know it's always going to go down. But what we could do is compare that, say, for men and women, or for different areas of Britain. You often find differences between London and the rest of the UK, for example. All right, now we get to a bit more interesting analysis when we introduce some covariates or explanatory variables. And there are many different types of event history model that you can fit. And crudely speaking, there are three main sort of factors to take into account when you're choosing the method. The first is the assumptions that the method makes about the shape of the hazard function. So in that previous example, time to first partnership, you saw that the hazard increased and then decreased. All right? And that's quite a common sort of pattern, but there are some event history models that force the hazard to either increase or to always decrease. So they wouldn't be appropriate in this situation. The other factor is how you treat time. Now, of course, somebody could partner any day of the week. So we would think of that as a truly continuous process. Right? But in practice, because these data are collected retrospectively, the data will actually be measured in discrete time. And in the NCDS, people were asked to report their dates of partnering to the nearest month. Right? It depends how sort of, salient the event is to a person. Sometimes they might be asked to record the event to the nearest year. So in that case, the measurement is in discrete time, even though the process that we're studying is in continuous time. The other factor to consider is whether the method will allow you to let the effects of covariates change over time. The standard assumption is something called proportional hazards, which I'll go on to talk about later. Another consideration, which I haven't mentioned there, is that we want to also allow typically for time-varying covariates. And that can be done using most event history methods, but it's easier with some than others. So I'll start by talking about probably the most widely used event history method, named after a statistician called Sir David Cox, the Cox Proportional Hazard Model, and that was introduced in the early 70s. And just to go through those 3 points that I had on the previous slide, it makes no assumption at all about the shape of the hazard function. So it's extremely flexible. And it's often called a semi-parametric method because of that. Okay? It doesn't make these distributional assumptions. It treats time as a continuous variable. And in its usual form, it assumes that the effects of covariates are constant across time, although it is possible to adapt that. All right, so this is what the model looks like. What we're modelling is the hazard function. So that appears on the left-hand side of the regression equation that we're going to be fitting, which is down here. Then you've got a covariate, x, and at the moment I'm assuming that that is fixed across time for a given individual. Okay, so that's why I only have an I subscript on it, and that's got a coefficient beta that we're going to estimate. And then you've got something called the baseline hazard, and that plays the role of the intercept that you have in standard regression analysis, but this can now depend on t, all right, because the hazard can change over time. So it's the hazard when all of your covariates equal to 0. And the model is very often written in this form, and you can see here we've got the exponentiated function of the covariates x. And that is to force the hazard to always be greater than 0, 0 or more. All right. And sometimes what people will do will take logs of both sides, and that gives you something that looks a bit closer to what we're familiar with when we see a regression model. All right, interpretation. What people usually interpret is the exponential of the coefficient, because that has quite a nice interpretation as something called the relative risk. Now, if that quantity was equal to 1, that would be saying that increasing x leads to a multiplication of 1 in the hazard. And if you multiply something by 1, you're not changing it, right? So 1 implies no effect at all. If that quantity is greater than 1, that implies that we have a positive effect of x on the hazard. And if you've got a higher hazard, that means that you're having the event sooner. Right? And if you've got a relative risk that is less than 1, then that means you've got a negative effect on the hazard or longer durations. All right, now here we have the results from fitting a Cox model, and all we've done here is added in gender as a dummy variable. I'm just going to skip straight to this quantity here, that's the relative risk. So what you can say is that any age, women are, the hazard of partnering is 1.5 times higher for women than it is for men. So in other words, women partner earlier than men. But what we're doing in this model is assuming that the difference between men and women is exactly the same across all ages, and that's the proportional hazard assumption. Incidentally, you can carry out tests on these coefficients just as you would in a standard regression model. So here you've got a p-value, and then you've got a confidence interval for your relative risk, and you can look at both of those to see if the gender difference is significant. So here you can see the p-value, it's very tiny, so you would say there was a significant difference between men and women in their the timing of their first partnership. All right, I just want to quickly introduce you to another approach which is very common in social sciences. It's called discrete time analysis, and that's trying to recognise the fact that although the process is often continuous, the measurement is often discrete time. And to fit a discrete time model, and there are a number of advantages to this that I'll just mention very briefly, you have to restructure the data. So here's an example. You've got two individuals. This person here partnered at age 21, and we know they partnered because the censoring indicator is equal to 1, whereas the second person, they were still unpartnered at age 33, which is when we last observed them. So they have a value of C of 0. What you have to do is expand the data in this form. So you have a record from age 16 up until they have the event or until they're censored. And then what we've got here is a binary indicator of whether they experience the event, whether they've entered a partnership. So this person here, string of zeros until we get to age 21, whereas this person just has a string of zeros all the way through because they never had the event. Not up to age 33 anymore. And then, having expanded the data, that variable y becomes your dependent variable. And it's a binary variable, and you can just analyse that using logistic regression. So that's one of the main advantages. You can actually, having expanded the data, just use a technique that probably you're familiar with already. Right? So you don't have to learn about the Cox model. There are other advantages. It's very easy to incorporate time-varying covariates. And it's also more straightforward when we cover more advanced event history methods, for example, to allow for repeated events, to allow for that, because it means that we can just use existing methods for analysing binary data. All right, so this is just an example of a discrete time analysis. I've got my female dummy in, as I had before, and now I've got a time-varying indicator of whether somebody is in full-time education, yes or no. And in a discrete time approach, you need to choose the form of the baseline hazard function. And two approaches you could try: a step function, that's essentially just treating time as categorical and fitting a dummy variable for each interval or for groups of intervals. Another approach is to fit some kind of polynomial function, so we might fit a quadratic. Now, if you think back to the hazard of first partnership in the NCDS, you saw it was up and then down. Now that can be quite well approximated by fitting a quadratic. Right? The t-square term allows the hazard to come down again at the older ages or longer durations. All right. Now these are the results from fitting dummy variables for time, and we've actually got 17 of those. We take age 16 as the reference category, so going from age 17, which is what T1 is here, all the way down to age 33. And if you look at those, you can see that the pattern is really following the pattern of the hazard plot that we had earlier. So we've got an increase up to around here, which corresponds to sort of late 20s, early 30s, and then it goes down again. And again, we can see a positive effect of being female, so in other words, females are partnering earlier than men. And also we can see that if you're in full-time education, we've got a negative effect. So those in full-time education are less likely to enter a partnership at any point in time than those who are not in full-time education. All right. And that is just a simpler form of the model where we're fitting duration using this quadratic form. We're just including t and t squared, where t is the variable in the expanded data set that was going from 16 up to 33. Well, 33 if they were observed for that long. 16 to 21 for the first woman. All right. So very quickly, just to end with, talk about non-proportional hazards. So I've said that so far we've assumed the effects are the same for all values, effects of a covariate the same for all values of t. And we can relax this, and all we need to do in a discrete time model is include an interaction effect between age, t, and between x. So what we've done here is to consider two models. The first is the main effects model, which we've essentially just shown earlier. And then the second one is where we've added interactions. And what we want to do in this non-proportional hazards model is allow the difference between men and women to depend on what age you're looking at them. So what we've got here is a plot of the log odds of partnering from this discrete time model. And if you look at any given age, look at the gap between men and women. Right? So you've got women on the top there in green, and then men in blue. Any age, compare them, and you can see that you've got exactly the same gap at every age between men and women. Now we move to the non-proportional effects, and this turns out to be significant, and you can see that the gap is large at the young ages. Okay, so it's a higher hazard for women because they're partnering earlier. But then as we move towards the mid to late 20s, you can see the gap is pretty much disappearing. There's even some suggestion later on, and you don't have many observations by this time, that actually men are partnering later. So if a woman sort of waits until her late 20s, then her chances of partnering at subsequent ages are exactly the same as they are for men. All right? There's very little difference between them. Right? So we call that an example of non-proportional hazards. All right. Okay, I won't go into these in detail. I'll mention the first one though, because this links directly to Bill's talk on multi-level modelling. So I've just looked there at the time of the first partnership. More generally, you might want to look at the formation of subsequent partnerships, because people have more than one partner over their life course, generally. So that leads to what's called repeated events, and what you can analyse there is the episode from leaving a partnership to forming a new partnership. And we can think of that as a multi-level data structure because you've got episodes nested within the individual. All right? And those episodes, those durations, are likely to be correlated if they come from the same individual, because there's going to be some characteristics of the individual that you haven't observed which could be affecting their chance of partnering at any age. So I won't go into these other ones. I'm going to finish now just by suggesting a few references you might want to have a look at. The first one by Singer and Willett, that really goes through in a lot of detail the discrete time approach. They also have a book called Applied Longitudinal Data Analysis, and half of that book is on the discrete time approach. So that would really be the place to start. And then there's a book by Hans-Peter Blossfeld and Gert Roher. That's actually been updated as a 2007 edition, and that takes you really right the way through different kinds of event history modelling, including the continuous time approaches, and the 2007 edition applies all that in Stata. All right. Okay, I've run out of time.
Okay, so we've got until 10 to questions for Fiona.